All right, so today's study group, the topic is on A/B testing, but I did want to spend a chunk of it talking about the coding out of a power analysis. So the structure of today's study group will be, first I want to talk about this power analysis lab and what all of this is for. And this is actually code that I mostly copied from the power analysis lab. I'm just going to walk through explaining that. And then I'm then going to talk about quickly explaining this example in the A/B testing lab. I think some people have some things to clarify, and so while I'm talking about those specific things, do let me know if I don't hit on them. And then finally, I wanted to walk through, let me just scroll down, here we go. Wanted to walk through the A/B testing with the data frames just to show in practice how you would actually do something like this. Cool. Before I get started, any other questions? Awesome. So this is the first time we've seen a notebook in a while. And we're going to start with power analysis. So with power analysis, it's usually one part of four things that are very intimately connected to each other. So those four factors are sample size, effect size, alpha, and beta. So we saw that that little flash animation that you can adjust either one and it'll solve for the other. So basically, if you have three of them constrained, you can solve for the other. So because of all of these constraints, we can do some sort of analysis to see, all right, if I were to adjust one of these or two of these factors, how would that change my experiment? So when do we do a power analysis? Usually we want to conduct a power analysis before we even do the experiment. So this power analysis is to really test, find out, all right, before I conduct my experiment, I do want to know the power of my test. Let me know if that doesn't make sense. But before you're actually going out and conducting your experiment, you want to know how reliable your experiment is going to be. And that's what a power analysis is done before you actually do any of like the statistical testing. So these are all the things that you actually have to measure before even starting to statistically to test this, get the test statistics and doing all of that stuff. And this is actually done with simulations, very commonly done with simulations. So power analysis, one way that you can, I think in one of the previous labs in power analysis, you can determine the sample size required to detect an effect of a given size with a certain degree of confidence. So here you can see we have sample size, effect size, and significance level, and then you can have different levels of power. So in other words, it allows you to determine the probability of detecting an effect of a given size with a given level of confidence under sample size constraints. So as I mentioned, given any three of these four factors, you can easily determine the fourth. One method that we'll be using is actually the power solving formula, which we'll see later that basically, if you have any three out of four of these constraints, plug them into that method and it'll solve for the fourth. And that can help you determine thresholds or things like that. I always find that it's easier to understand these things with a scenario. So let's set up the scenario to start. So this scenario, a researcher wants to study how daily protein supplementation in elderly will affect baseline liver fat. So the study budget allows enrollment of 24 patients. So here we already have our first constraint. We're constrained by our sample size. So half will be randomized to a placebo group and half to the supplement treatment group, and the trial will be carried out over a month. And it's desired to see whether the mean change in the percentage of liver fat from baseline to the end of the study differs between two groups in the study. So basically, over a month, 12 out of 24 of the patients are going to be given the drug, 12 are going to be given a placebo, and we want to see if there's going to be a difference in their baseline liver fat. So the researcher needs to know what power will be obtained under the sample size restrictions to identify a change in the mean percent liver fat of 0.17. Based on past results, a common standard deviation of 0.21 will be used for each treatment group in the power analysis. So first of all, we have our hypotheses, right? And this is a two-sample t-test. We have one group that's getting the placebo, one group that's getting the drug, and we just want to compare and see if there's a difference in their liver fat. Yeah, liver fat. And we have our alpha set at 0.05. So in this situation, they have an effect size that's already determined. They want to see, or they know that, all right, for this drug to be effective, we want to show a 0.17 difference in this liver fat percentage. So that's another constraint. What we have constrained here is the difference that they're looking for. And in this case, this would be our effect size. Oops. Our final constraint that we have here is our alpha of 0.05. So I think, yeah, here it says, in this experiment, we're constrained by sample size, effect size, and alpha. And this code that goes on after this is the hard coding of determining the power of the test. And I think is a good way of just showing like how that number is, how we get that number for power. So power of the test is the proportion of simulations where the null hypothesis is rejected. So if we remember the definition for power of a test, and let me actually bring up the slides from yesterday. The power of a test is defined as the probability of rejecting the null hypothesis when it is indeed false. So for these cases, we are assuming that yes, the null hypothesis is false. So what they're doing here, and I think as I go through it and explain, it'll make a little bit more sense. So with this first block of code, we're just defining everything that we have. We have our sample size, which is 12, because there's 12 people in each group. We also have, this is the information for our control group. We have a control mean, and we're going to actually start at 0 because they don't have an actual, they don't tell us what this number for, what is it again? Liver fat. They don't give us the number for liver fat first. So we can just say this is 0. Standard deviation, we're actually using the common standard deviation. This is something that is just derived from context or derived from past experiments. Depending on the situation, you may or may not have this number. And then here we have our experimental group. So in this case, we are now going to say that yes, there is a difference of 0.17, and we're going to run simulations to see how many times this null hypothesis is actually rejected. I'm going to repeat that again. This experimental group, and this is the group that was given the real drug, they are expected to see a mean of 0.17 because we are using simulations of an experimental group that indeed has a difference. And by taking the proportion of times that the null hypothesis is rejected, that gives us the power of our test, because the power of the test is rejecting null hypothesis when it is indeed false. So here we're going to actually start with the experimental group being indeed false, and there'll be a little bit more setup to this, and we'll see that happen. And then here, number of simulations, we'll do 1,000 for more, 1,000 for now. If you do more simulations, of course, it'll be a little bit more accurate, but I think 1,000 is enough to show what we're doing here. So I think this block of code is a little bit intimidating, but let me just break all of these down. So first we have our random seed, just so that we have reproducible results, but also across all our notebooks, we'll have the same numbers. Here we're gonna initialize this array to store results. This is just one way of doing it. Often you can also start with just an empty list and like append your results, same thing. So here they're just starting with an empty list and filling it with NaN values. So this is the for loop that does simulations. So I think in setting this up, maybe it'll make a little bit more sense. So what we're doing here is we're generating our random samples. So what we're doing here, this numpy.random.normal line, that actually picks numbers from a normal distribution with the parameters of your mean and standard deviation defined here. So in the control group, it's actually going to make a normal distribution that has mean of 0, standard deviation of 0.21, and pick 12 numbers out of that based on like the probabilities of a normal distribution. For this experimental group, they're going to do the same thing, but instead of 0 mean, they're going to have a 0.17 mean. So on average, your experimental group already should have a higher, like roughly 0.17 higher numbers than the control group. So this part, these two lines, are confirming that, you know, the null hypothesis is indeed false. It should be rejected in all of these situations because we are pulling it from those distributions. Does anyone need to clarify any of that?
Could you just explain that again? I
Yeah,
didn't understand.
Of course.
Yeah.
So the whole idea of doing this power analysis is we want to see how reliable our test is. And so we're setting it up, we're setting the simulation up in a way that these two samples that we're creating are going to be drawn from two normal distributions that have a difference. So therefore, you know, if we're pulling 12 each from each of these normal distributions, we're pulling 12 samples each from 12 people from each of these groups that should have a 0.17 difference. And because of, you know, the distributions of this control group and this experimental group, they basically represent the group that doesn't have the drug and the group that has the drug. So these are not actually the groups that have gotten the drug and haven't got the drug. They're just simulations representing. These should be the people that didn't get the drug, so their change is 0. And then this experimental group is going to be the group of people who got the drug and the drug worked and had a difference of 0.17. I don't know if that helped or not.
Yeah, that makes more sense.
Okay, cool. So basically, because we've set up these two samples in a way that that the null hypothesis should be rejected, we're going to actually run simulations to see if the null hypothesis is indeed rejected every time. So after setting up these two samples, all we do here is you run a 2-sample t-test. With this 2-sample t-test, this is going to be the student's t because same standard deviation and same sample size. When we run this, we will get a t-statistic and a p-value. So when you run a t-test this way, stats.t-test independent actually returns you both a t-statistic and both a p-value. And it's in a tuple. And so for the p-value, we're going to just take, to get the p-value, we're just going to take the second part of the tuple. And so after all of that is filled up, we're then going to look at, all right, how many times is the p-value actually less than 0.05? I think it'll be a little bit clearer after I run this. Oh my gosh, there we go. Okay, so here we see we end up with a power of 495, and let's see like where that comes from. So things we can look at, let's actually take a look at, let's look at P. So this array P is going to be all of our p-values taken from 1,000 t-tests. And these 1,000 t-tests are done on 1,000 different pairs of samples drawn from these two distributions. So because we don't know like the actual people who are going to be in the experiment, we're just drawing random samples of 12 from these two distributions, conducting a t-test and taking a look at all of these p-values. And the power of this test is the proportion of p-values that is actually less than 0.05. Because those would be the times that, you know, we correctly rejected the null hypothesis. Anything to clarify? Awesome. So that is the power of a test.
One quick question.
Oh, absolutely.
Now, you wouldn't necessarily have to do all this to get the power, right? You could just plug it into a formula, right? Or a calculator.
Yep, absolutely. I'm just about to show y'all the code over there. But yes, typically, this is kind of how power is generated. It is looking at the proportion of simulations that correctly reject the null hypothesis. But yes, we do have it built in. I think it's just good to know how those numbers come about. Yeah, anything else before I just talk about really quickly, talk about this, this next step?
So it says that there is a 49% chance that we don't have type 2 errors.
That we don't have type 2 errors. Yes, yes. So that's right. There's a 49% chance that we don't have type 2 error. So that means there's a pretty much 50% chance that we do have a type 2 error, which is not great.
Okay, thanks.
You're welcome. Anything else? Yeah, I will say this, when I was learning stats, this whole idea of like doing simulations did take a little while for it to sink in. What helped me is just thinking about this as like, all right, this is before you even conduct the experiment. You want to look at what kind of, like, how reliable is your experiment going to be? All right, I think this is kind of what, if we ever do need to do a power analysis, this is what we will use over, you know, this simulation. But we have this t-test independent power formula, which is really, really useful. First, you actually have to instantiate it. I don't know if we've come across anything like this yet, but we will, once we get to linear regression, we're gonna instantiate power. And then power is a variable that now has all of the attributes within this. If that didn't make sense, don't worry about it for now. And then we can solve power. So in the solve power documentation that we have here, you can see that you can give it all of these parameters: effect size, knobs is number of observations, alpha, power, and a bunch of other things. And basically it will solve for any one parameter of the power of the two-sample t-test. So right here, all we need to do is plug in the values that we had as constraints. So 3 of the constraints that we had were, here they're looking for sample size. Actually, let's first solve for power. So let's do sample size, and let me check what this is. It is, I think it's knobs 1. All right. Equals to 12, and this should solve power and give us 495. Let me just double check that it's the same. Oops, what am I looking for? Knobs 1, number of observations is sample 1. There we go. I think it might be a little bit different because we have a one-sided versus two-sided, but as you can see, kind of a similar number. I don't want to go too much into this, but you can see you have a similar number for power. Yeah, I do want to take a quick look and see if the two-sided will change. Alternative equals to two-sided. Let me see. Never mind, I'm not going to go too much into this because usually you're not solving for power, you're solving for something else. So in this scenario, often in behavioral research, 0.8 is accepted as a sufficient level of power. And if we fit around with that animation that we had, the larger your sample size, the higher your power, just because you have a more representative sample. So we take a quick look at this. If we want to solve for power of 0.8, we can feed it in the alpha that we have and also the effect size that we're looking for. And again, remember, effect size, we do have to divide it by standard deviation for Cohen's d. Once we solve for this, you can see that we end up with a minimum sample size of about 25. So in order to achieve a power of 0.8, we should look for a sample size of 25. And that's actually something that we can plug in here in our simulation to take a look. So here we change our sample size to 25 instead, and we just make sure, I don't think there's anything else we need to change here. If I were to run this, you can see here our power becomes 0.81. So sometimes, you know, if you are constrained by power and you're not constrained by sample size, you can solve for a minimum sample size that you need. And of course, if you have a sample size greater than 25, it'll be even better. But often you are constrained by like, I don't know, costs of doing experiments, stuff like that. This last part is doing it in an iterative approach. This is basically running this, but for different sample sizes. I think it's easier after I run it to take a look and see what's going on. All they're doing here is they're doing pretty much the same thing that they were doing before, getting all this new data in the same way that we were doing prior to this, saving p-values and calculating the power through simulation for increasing number of samples. So this is just really what is happening in the back end of doing this. Questions? I will say that this code is less important. I would say like if you really want to get into the code, this one is probably a little bit more relevant. But any questions on power of a test? I believe that is all that I have for power of a test. Oh, and I guess we can quickly plot this.
When we change the sample size to 25, we get the sample of each of control and experimental 25 or both of?
For this case, it's each sample 25.
Oh, okay.
So altogether, you should have 50 people.
So for two sample size, it gets 50 out of both of them, right?
That's right.
Okay.
Awesome. And this is just the graph of like increasing sample size. We'll look at the effect of power.
I have a question. Just conceptually, in the setting up of this test, what we're testing is the mean percent change of liver fat, and it had to be a mean of something in order to like to assume a normal distribution, right?
Yep, that's right.
But it didn't have to be a percent change. We could have had like just a base number, like whatever your liver fat level is, and it increased.
Yeah. 17. Yeah, I am honestly not too sure how liver fat is measured. I assumed it was a percentage to begin with, which is why we have this 0.17 difference. That's what I assumed. Yeah, but I honestly, I'm not sure how like liver fat is actually measured. I honestly thought it was a percentage, which is why the 0.17, we wouldn't have to deal with, percentage change from like a certain level. But yeah, this kind of stuff, definitely, I think for most purposes, we're dealing with like absolute differences rather than percentage difference.
Yeah, I was just trying to think through if it was an absolute difference.
Yeah.
Then the effect size, because there was something in the documentation about effect sizes of 0.2 versus 0.3 versus 0.5 are small versus high. But when you're dividing it by the standard deviation, so like,
yeah.
If we divide the 0.17 by the 0.21, I mean, this is actually a really, really large effect size.
Yeah, so yeah, 0.17, pretty sure, I don't see why they would give us, because this was from the curriculum, I'm pretty sure that is an absolute difference. And then for effect size, because Cohen's d is measured by absolute difference divided by standard deviation. So yeah, it is a pretty sizable effect size. I think divide that will give you like a 0.85 effect size, I think. Yeah, so pretty big effect size, which is usually what you're looking for these like medical, for these medical tests, I think. Like you usually want to see a sizable difference in people who get the drug versus don't get the drug. But yeah, definitely like having contextual knowledge on these things helps. And hopefully in the future, if you do have to do statistical tests at your job, you do have the contextual knowledge of whatever it is you're doing the tests on. But yeah, anything else to just like round off like this power analysis section? Yeah, I will say that this power analysis and also like basically all the analyses of, experimental design, those are the things that I understood like maybe only my third, fourth time round of doing stats. So for me, it was a little bit less intuitive, just to let y'all know. All right, well, the next thing I wanted to talk about was not this yet, but the first example of A/B testing. I think Mark had asked about some of this, so I did want to just go through it really quick since there's a question and clarify what's going on here. we'll be honest, it's been a while since I've looked at this lab, so it might take me a little bit to figure out what's going on here. So, all right, let's take a look. Here, we're designing an experiment to test email templates and response rates. So currently there is a 5% response rate, which is great, but they're doing a new design that wants to look for a 1% performance increase. So they want to see whether, they want to see how many people they will need to include in their A/B test to detect a 1% increase. So here in this case, I'm not sure, they're probably solving for power. Your constraints are a little bit different. Here we are constrained by our alpha. We're constrained by our, actually no, the constraints are the same, what am I saying? You're solving for the sample size because you're determining how many individuals you need to serve the new email template to detect this effect size. This 1% performance increase, again, I want to assume that it is absolute because here they're also using 5%. So I don't know if they mean like 5.05 response rate or whether they're looking for a 6% response rate. I'm going to assume here that 6%, but we'll see if the code says any different. So first we have our hypotheses. Success for the new email template is 0.05. And here they're using 0.05, which is the same as the old response rate. So basically it's pretty much the same as saying mu1 is equal to mu2. And here you can see the probability of success for the new email template is 0.06. So yeah, any questions about this hypothesis? I think based on this hypothesis, we are looking at an absolute increase of 1% from the response rate.
Sorry, maybe I missed this, but how did they come to the point greater than 0.06% as like
how did they come up with this hypothesis?
Yeah, like the 0.06 number.
I think the 0.06 is because they're looking for a 1% performance increase over an already 5% response rate.
And is that just set by like the company, like their strategy would decide that? It's like subjective, right? We didn't calculate.
Yeah, this part is subjective. That's right. So this example, for them to make it worth it to serve this new email template, that's the difference that they need to look for. Very similar to the previous example, the last example where you wanted to have a difference of 0.17.
Okay.
So similar to that, that is something that is predetermined, especially when you are doing when you're in the experimental design phase.
Okay.
So here, what they're doing here, it looks like, let's see, we're defining alpha and beta. So here they're looking for an alpha of 0.05. I think, and a power of 0.8. So similar to before, they want to achieve a power of 0.8. And they want to determine what is the minimum sample size that you need to get a power of 0.8 in this test. So here, very similar what they were doing. Here they set the mean, okay, this is less important. Effect size, you have mean difference divided by standard deviation, same as what we did before. In the solve power function, they have alpha equals 0.05, power equals 0.8. Alternative equals to larger, that's actually because this is not a 2-sample t-test. This is a 1-sample test. So they're only going to give this new email template to one group of people and compare their response rate to the rest of the population of the people that are getting email templates. So I think this is one big difference between this experiment and the last one, which was a little less clear with the setup of the question, but yeah, I think that's something that I'm going to point out, that this is doing a 1-sample test. They're actually comparing this group of people who have gotten the new email template to the people who haven't.
And is it larger just because you're looking at the right tail? Because I know you can set it to smaller.
That's right. Larger, I think so. Let me actually take a look at this here. So extra argument to choose whether it is you're right, a one-sided or two-sided. So one-sided test can be either larger or smaller. Because we're looking for an increase, you're right, it is a one-sided test. we're looking for an increase in the response rate. Yep. So if you run this code, and I don't know if they have it, I don't think they have it output, but after running this cell, you should get the minimum number of people in your sample needed to detect this response rate. Questions so far? I think this next part is what's a little bit confusing.
Yeah, and then the number I got for sample rate was pretty high, like 280. And the numbers below were kind of different if you look at the charts that come out of the bottom part there.
Okay, actually, let me just clone this lab super quick so I can run it as well. We should be good on time, I think. Let's see. We have testing. I have this here. All right. Let's run these and see what happens. Should have done the solutions. All right, bear with me for a little bit. Let's copy this over so we can take a look. I don't think there's any other imports. Let's do that over to here. All right. Solving power, yeah, about 280. You do need to, so for this company to detect this response rate difference, they need to give their new email template to 280 people. Which if you think about a company giving out email templates, I guess that's not too many people. I don't know. I don't know marketing as well. All right, what else do we have here? Let me copy this over. These are our power curves. Go. So with these power curves, what's happening is we want to look at if we were to edit alpha and also edit the effect size, how will that affect power? So you can work with different constraints, and maybe depending on what you're optimizing for. So let's say you really cannot, you really can't like give this new email template to 280 people. Maybe you only have enough money to give out to like 200 people. How will these other factors shift because of that new constraint? So that's just an example, but here they're looking at how required sample size changes if you have different alphas. And then also I think they're looking at different effect sizes. One thing also I wanted to mention, because this effect size is fairly small, I think, or fairly, I guess, not fairly small. You're looking at a fairly large effect size, so therefore you're looking for, therefore it kind of makes sense that you need more people. Yeah. Okay, so these power curves, let's look for the example that matches this one, just to see how it goes. So we have alpha 0.05, an effect size of 0.11, and the number of observations they were looking for power would be, oh, okay, I see where you're getting at, Mark. I see, because they said 279, so 280. So that means we're about here. And this actually only shows us a power of 0.2 something, which, let me take a look at this code just to make sure what we have is the same thing. Yeah, did anyone else have any like questions about this lab? Let me just see what they're doing here.
What's the actual effect size? Because that one you're looking at was the 0.11, which is really small.
So here we're looking at 0.01 divided by the standard deviation. So the effect size is actually going to be quite big. It's actually going to be 0.01.
Sorry, it's 0.21, so it's a different line on that curve.
Yeah, that's what I was saying, because you were looking at the 0.11.
Oh, was I looking at the point? So this one? This is, oh, this is 0.11, not 0.01. Okay, I get it. I see. Yeah, I get it now. So The actual effect size should be, and actually let me see what they're doing with effect size here. If they're doing the absolute or if they're doing the, let's see, effect size, they are doing it divided by standard deviation, and they're doing different mu deltas in 0.01, 0.02, 0.03. All right, so actually, yeah, it should be this one. We are looking for the second one, which, how do we figure out which one that is? That would be, let's see, effect sizes here. So I think it's actually referring to this one, this second one, or is it this? Let me take a quick look. I think it makes sense for it to be this, but that also doesn't match up.
Yeah, by reading that, it looks like the 0.8, they only have like 75.
Yeah. There we go. So, so doing this calculation, the effect size that we're looking at is the 0.21 line. So yeah, that is my bad. So we're actually looking at the 0.21, which is this blue one. So this blue one at 280, we are looking at roughly, all right, roughly 0.07, which is closer to 0.8. I just want to see how many simulations they're not doing simulations. They're just straight solving, right? Yeah. Power. Yeah, so Mark, your question was that like the numbers just didn't match, right?
Yeah.
It could be that they're not doing, it could be that they're not doing like the same test. Like, I'm not sure if they are also doing the same like one-sided test. I think that could also affect it. I would have to like dissect this code a little bit more. And I'm also personally not super sure where this like how this plot power works, because power analysis is here solving this power.
Okay, that's all right. We can move on.
Yeah, but yeah, the number doesn't match, but it might have to do with the way that this is being determined, because it does depend on how this is being solved. But yeah, I'll look into it a little bit more and let y'all know if I find anything. But yeah, this is an interesting one to look at.
On that one, they didn't define just one tail, so I don't know the syntax for it, but
yeah, that's what I was thinking as well. So since we're here, stats models, power, let's see. So I wonder if you can give it, yeah, I'm not sure. I would have to look more into it just to see if you can do like one-sided two-sided tests. I think it would be under these, but I'll have to do a little bit more research. But yeah, just to close out this, any other questions that maybe I can also look into after this? All right, cool. But the process of this is very, very similar to the process of doing this. So yeah, just wanted to let y'all know that. Okay.
Because we are using Cohen's D, we should use we should do the hypothesis quantitative.
Oh, like you're saying for when you're setting up these hypotheses, as they did say like these quantities?
Yes.
I do think for the hypotheses in this context, this is not the only way. I think for hypotheses, you usually do want to use the actual number rather than the effect size. I think it wouldn't make a big difference if you did like effect size is 0.21 versus effect size is less, if you do effect size is 0.21 or effect size is greater than 0.21.
Because it uses them for the mean difference.
Yeah.
Right below. The mean difference is 0.06 minus 0.05, yeah.
Yeah. I think like one other way you could do this is that you could also say that like, for example, if you want to represent it by like X bar, with this sample. You could say X bar is equal to 0.05, but here you could be X bar is equals to 0.06 or greater. So I don't know if that helps. But I think that in the formulation of these hypotheses, the syntax or like the actual words that people are using in the hypotheses can differ, and it wouldn't make a very big difference. But you can look for difference in, you can say like difference between sample and population is less than 0.01. Here you can say difference between population and sample is more than 0.01. That's also something that's a possible hypothesis.
Okay, thank you.
You're welcome. All right, let's see. All right, let's talk about the last A/B testing example. This is a little bit more applied because we're using like actual data from a data frame. So if anyone has gone through this and has any questions, do let me know. But imagine we have this data frame here. I believe the context is you have some sort of change to a web page. So here you have all the unique IDs. You have different groups. So usually in A/B testing, and very commonly for like websites or apps, new changes are rolled out to only a proportion of users. So here you can see that like some IDs were given the experiment, which is like the new change to this web page, and some people were given this control. And the idea is we want to see whether this new change led to more clicks on a website. And so you can actually, in this preview of the data frame, all we see is view, but we'll see that there's some of them that are clicks. So for this, let's do a really quick EDA. Just doing a bunch of aggregations on this data frame, the number of people who view, 6,000, number of people who click, 1,800, the number of viewers who didn't click, this is just really this minus this number of clickers who didn't view, 0, which makes sense because if you don't view, you can't click. This is just some of the EDA that was provided. For this, let's split up our data frame into the control people and the experiment people. And let's do a quick value counts. So the control, so the people who had the old version of the web page, about 3,300 views, 900 clicks. So in the experiment group of their actions, we have about 3,000 views as well, and then also about 900 clicks. So just by looking at the numbers doesn't really look like a huge difference, but let's take a look like statistically whether there is a difference. I believe this is just a little bit of data manipulation to make it easier to count, to just add a count column so that you can add up the count formulas, add up the count of different rows. So here you can sort of see your sample sizes. Control, we had 33 samples, yeah. Control, we had 3,300, experiment about 3,000. In terms of number of clicks, these are numbers that we already saw. The one we're really looking at is this click rate. So we have this click rate for the control group of about 28%, and for this experiment group, about 31%. And so what we're gonna look at now is whether the control group and experiment group have a significant difference in this click rate. So this straight up is a 2-sample t-test. We're just comparing 2 groups of people. I'm gonna do this 2 ways. Exactly the same, I will say. These are the t-test formulas from the old labs that we had for like defining like Welch's t-test. After running this, you can see that we end up with a p-value of 0.008, which is less than our alpha of 0.05, so we reject the null hypothesis. I think this is the code that the lab has you do. Really quickly, I also wanted to show you all the built-in function so that you don't have to define all of these formulas. So this is the built-in function from not stat models, from SciPy, that you literally give it the same information. Because it's a Welch's t-test, you got to tell it that equal variance is false. And when we run that, you can sort of see we have this t-statistic here, but we get almost the exact same, is it the exact same? Almost the exact same p-value of 0.008. So either way, we can reject the null hypothesis, and we can pretty safely say, that this new change to this web page results in a higher click-through rate. Questions about this? I will also say that like with data science, things like this, things like A/B testing, is one of the more likely applications of statistics that you would use in a job, because A/B testing is something that if you end up doing a role in like marketing or in anything that has to do with an app, if you're like testing different features, you would be doing two-sample t-tests or A/B testing. Cool. Any questions? Awesome. I will say this kind of does wrap up our statistics section of the phase, which I'm very excited about. Tomorrow's study group will be a little bit of probability, a little bit of talking about different frameworks of probability, as well as maximum likelihood estimation, which is kind of a very like big picture look at what modeling means. So that one's going to be very conceptual, but does set the stage for what we're doing next. Yeah, any questions about anything so far? I will take a deeper look into the code for this lab and then send any updates if I find anything. All right, well, if there are no questions, I will see you all at your one-on-ones or at tomorrow's study group.
I have a question.
Yeah.
Quantile method on pandas.
Uh-huh.
I don't know how it works. I read the documentation, but I didn't figure it out.
All right, let's take a look. Pandas quantile looks like returns values at a given quantile over requested axis. So what I think, I have a guess of what it's going to do, but I'm not too sure. 0.1. So what I think Quantile does is, if you're taking the quantile of a data frame, and for example, here you're looking for like the 10th percentile or quantile, it gives you the value that is like at the 10th percentile of this, I think. Honestly, we can try it out. Let's try it out real quick. Let's do it over here, and let's see if this data frame makes sense. Let's pretend that the ID column is something that we want to use. So let's see. Okay, so let's do df.id. And how do you use it? .quantile. All right. Where was it? Here. And the default argument is 0.05. So let's see that. So for ID quantile, here you got that, which is 566,000. If we do a df.describe is the one that we want to see. There we go. If we do a df.describe, we see that this quantile gives us the middle value. And if we just quickly want to look at and see what this ID column is, of course, ID doesn't mean anything in this context, but I think if I do, does that work? There we go. So these are like what our, how our IDs are spread out. If we do like a quantile of 0.1, we're basically looking at, all right, if we had like a cumulative distribution function, where in our, what value will be like the 10th percentile of values. Does that make sense? So basically, if I were to do like 0.25 here, 0.25, which is 373, corresponds with this value. It's like the 25th percentile. And I think you'll be able to put in any decimal number. I think if you even give 1, I don't know. Yeah, if you give 1, it'll give you the max value. So yeah, that's what Quantile is. It is helpful for if you ever want to like bin your values. I've seen people use Quantile to bin values.
Would you just take like the ID and set them to new IDs? So like, or a new value. So like df.id for the 25th percentile. Sorry, my English is bad.
Oh, good. So like what you mean is like if you want to like bin your values, right?
Yeah, so if you're wanting to bin your values, would you just set a new variable equal to the quantile 0.25 and then
not, you can't do it just like that, unfortunately. I think you would have to do something like, I don't know if there's something already built in, but let's say you want to do it like by like your different quartiles. Like you want to bin everything below, between this value and this value, between 25 and 50, between 50, 75, 75 and max. If you want to do that, I think you would have to like literally go through, all right, if it's between this and this, replace it with df.quantile 0.25. And replace it that way. I'm not sure if there's a better way to do it. I have a hunch that there might be, but yeah, you would like, probably the way I would do it is do like a dot apply and, or a dot map to change the values. But yeah, that's cool. I haven't looked at dot quantile in a long time, so thanks for bringing that up. Yeah, anything else? Cool, sounds good. Well, tomorrow we'll be talking about Bayesian stats. Friday, we finally get into linear regression. Yesterday, I did mention really quickly about like the mini assignment that I wanted to give out. So I'm gonna actually like type that all out and send it to the channel. So do look out for that. And I will say that assignment will really only make sense after Friday for those of you who haven't gotten to topic 18 yet. But hopefully we'll get that, that can be done over the course of next week. Cool. If there are no other questions, as I said, I will see you all at tomorrow's study group or at your one-on-ones. All right, have a good rest of your day, everybody.
Thank you. Bye.
Bye.